with an exercise. Okay. So thank you for having me come here. Thanks for the invitation, and thanks for coming back this afternoon. So my name is Werner Krauth. I'm theoretical physicist at the ENS in Paris and also at University of Oxford. I have had a long-standing interest in computational physics and computation in general. So the subject I will discuss, I can also speak up as a and then I'll walk around you. So then, anyway, so the subject that I want to discuss is, as shown here, is the second Markov-chain revolution. I will explain what it actually means very quickly, and let's say my main interest in talking to you is to get you involved in doing many things yourself. You'll see this very quickly. So today I have a project of 16. Well, he's already laughing with Patrick. He knows me, and Gabriele, where is he? Gabriele knows me also, so they're already laughing. So I have a little project for this afternoon. For this, so I have a who is going to be the president of the session? No, you've already. So I need the president of session to. Is that you? So then you stop me after 40 minutes. So I have to stop at 40. At 35, you tell me that it's 5 minutes, and at 40 you stop me. Because I'm just like the others, and otherwise, we'll be here until tonight. And then we have a 10-minute break, and you make sure that we are out of here. I mean that only the super enthusiasts remain here at 4 o'clock. So give me another warning at 5 to 4, and then we stop. Right? That's the way we do it at home. So I have a project of 16 little programs that we may not do all together today, but I mean, so these are 16 computer programs that have between 5 and 7 lines of code. You're not obliged to do them with ChatGPT, just to bring out the devil. But anyway, so they will introduce you to some of the subjects. So let me just start with, so this, what I'm interested in is, for this week, I will be interested in discussing Markov-chain Monte Carlo methods, which are, so first question you may ask, why am I speaking to here? It's because this is a school of the statistical field theory and its permutations. Right? Statistical field theory and its permutation. One of the permutations of statistical field theory is the theory in the field of statistics. So I'm more in the theory of field of statistics, but of course the methods we are speaking about are absolutely everywhere. What I'm speaking to you is going to be of interest to you if you are in statistical field theory or in the field of statistics or in many, many fields. What I'm discussing you is one of the bedrocks of science. It's based on one of the most cited papers in all of science, which is the paper of 1953 of Metropolis et al. And I want to give you an introduction to this whole field. So the field that I want to discuss is the field of Markov-chain Monte Carlo. Is an outstanding tool in science. I'm just reading the introduction I gave here, and which consists in evaluating integrals in high-dimensional spaces. So now, this was introduced, as I told you, in a paper in 1953, Metropolis et al., which introduced the concept of sampling. This was a big revolution, and we want to live again this revolution. This was the first revolution. So for a long time, it was understood that we could do integrals by doing them, as you have seen this morning, as we could do them as we have learned all over in our lives. We could also do these integrals by sampling. And the reason why we are speaking about this in a physics context is because it was understood, because this revolution, this first revolution, understood that we could map many integration problems into a fictitious physical system in thermal equilibrium. So we'll go through this in detail. So this was mapping any problem in the hard sciences, in the social sciences, in many, many problems. We were able to map this into a fictitious problem of equilibrium physics. Then I can give you exactly also the dates, about 25 years ago, it was understood that we could go beyond this picture. And we could go beyond this picture, and this has given rise to what many people call a revolution. Of course, any revolution is immediately when you have something like this, there are many people say there was no revolution. It was just, it doesn't exist, but let's call it like this. And this revolution consisted in much better understanding of what we were actually doing. Not some kind of intuitive mapping onto equilibrium statistical StatMech. So this goes by the names I put in the announcement of mixing, stopping, coupling, lifting, and other models. They have given a much better understanding of the sampling approach, and they have given much faster, sometimes even perfect sampling approaches, and have brought in also the concept of non-reversibility. We will discuss that in detail in the next few weeks, and have mapped not on equilibrium statistical physics, but on non-equilibrium statistical physics. So lecture 1, we are not yet there. Lecture 1 on Wednesday will be on mixing and stopping, just to give you these names here. Lecture 2, so this is on Wednesday. On Thursday, I'll have lecture 2, which will be on coupling. You'll become big experts in all these fields. Lecture on Friday will be on lifting. So now, so this may sound, this is of course maybe less understood than bosonization, but or less common than pop. So these are the concepts I will discuss. I'll have lecture notes if our initial enthusiasm continues, and so I'll eventually have lecture notes. But now we are in number 0, and I want to discuss the concept of sampling. That's where it comes from. So this is not part of the revolution, but that's what we actually have to understand. What does sampling actually mean? So now, instead of giving you a long introduction to the sampling, so I will just start. I'll start with some of the exercises, and then maybe we just make a little break, and you discuss, or we don't make a break. I mean, I'm completely flexible with my time. Not completely. I mean, I'm under your right. I mean. In the limits, with my boundary conditions, I'm completely flexible with what we want to do. So first of all, I have to say sampling is something sampling is simply it simply means exampling. So it's a short version of examples, taking examples of a probability distribution. But let's not do it like this. Let's do it in an example-based way. And I have the first example of 16, which is sampling a uniform distribution. Maybe we don't have to do this. We don't have to do that on the computer because it's really too simple. So we take a uniform distribution in 2 dimensions, and excuse me for Patrick and for Gabriele, you've seen this before. We have a uniform distribution between -1 and 1 in x, between -1 and 1 in y. Let me do a little circle here. And we have a distribution that we want to sample, which is x, y, which is equal to 1 if xy is inside the square. All right, so let's write a little program. Let me do it just so. Let me get started with what I really like to do is making things concrete. So let me write the first procedure, and it's called direct pi. I'll explain that immediately. So what we do is, so that's the way I write these things. For take x random between -1 and 1, take y random between -1 and 1 and 1. And then let's do something more useful. So then we say that here if x squared plus y squared less than 1, then do n hits plus equals to n hits plus 1. And then at the end, we do an output of n hits. So that's my program number 1. So what does it do? Maybe you can read it. You can read it off. It's completely trivial. But what does it do? It generates. So I suppose that there's a random number generator. We don't get into details between -1 and 1. It gets pebbles. It gets points in this square uniformly, and it computes hits if they are inside the circle. So you know what this program. What does this program compute? It computes the area of the circle. It divides the area. It computes the area of the circle. That's not completely right. Okay. So it computes the area of the circle divided by the area of the square. Can you give me what it does? What does it compute? How much is that? Not quite. Just program it and you'll see it will not come out to be 2 pi over 4. Okay, so this will be approximately pi over 4. So this is a way of computing pi over 4. Okay, so now you are invited to program this if you want to, but maybe we can do this later after. We can even do that after having had a few grappas tonight, right? So so this is. But you see already. I mean, we can have hour-long discussions on this problem because it's not so easy. So what are we doing here? We are sampling an integral. What is the integral? So we compute the integral dx dy pi of x y times an observable of x and y. And you said already we have to divide it by integral dx dy in the square. And O of x and y is 1 inside the circle and it's 0 outside. So effectively, that's the understanding that that the sampling approach brought in 1953. That's a long time. None of us was around. Yes, I think none of us was around. Okay, so this is the understanding that we can do these integrals. We can do integrals like this by a sampling approach. Okay, and we wrote this as 1 over n sum over I OI. So now let me get to the second example. Again, this is very simple, but as I understood this morning, that not everybody has spent their whole life doing Monte Carlo calculations. Right, so far I've understood this morning. So maybe let's do a sampling algorithm 2 of 16, which we call procedure Markov pi it's the same example, minus 1, 1, minus 1, 1. I start up here at 0.11. If you want to have the whole story and the, this is decorated, the story can be decorated. If you look into my little book, I wrote a book. It's widely available on Russian websites. So you can, no, it's not a joke. It's actually, I mean, it is. We have no sense of humor. I mean, right? We are physicists, so it is widely available on Russian websites. Period. Please use it. Okay. So we start here. And we throw. If there's a story to it, we throw pebbles. Then we go here. We make a random walk. And we make a random walk in this square, and we play the same game. Okay, so we throw pebbles. In the interest of time, I don't make the picture. Let's do it like this. Let me show the picture. The n hits equals to 0. X and y is equal to 1, 1. For I is equal to 1 to n. Do the following. Choose a delta x random between minus delta and delta, right? Random minus delta and delta. If x plus delta x smaller than 1 and y plus delta y smaller than 1, what do? We go to x is x plus delta x, y is equal to y plus delta y. Then what we do is, if x square plus y square less than 1, then do n hits plus 1. At the end, output n hits. You know what's coming on now? So what does this program compute? Pi over 4. Well, 2 pi over 4 would be a wrong answer. But do we actually understand? So now I'm interested, can ChatGPT translate this into when you take a picture? No, I'm just asking the question. It's an associated research question of whether, we can get it automatically. Anyway, so what are we doing here? I think we are getting into deeply less understood questions than we had before. So we are, let me make a big picture here. So we are at some point, we are at x and y. What do? We choose a little square of size delta. Okay, you see this? What do we do then? We choose a random point in that square. Okay. And then if we haven't fallen out of the square, we actually go there. So we make a random walk. The random walk is a concept of equilibrium statistical mechanics, and that is the mapping of a computing problem, because we have a computing problem, computing pi over 4. So we mapping this. So now we are mapping our problem onto this thing. But there's a lot of subtlety in this program here, because something can happen. I'm at position X here. Okay, so this is, you see this? That is my square, plus 1, minus 1, plus 1. So I'm at position X. I'm throwing a, I'm getting the next sample. The next sample would be like here, and it could happen that as I put the position that I'm proposing. So X. So this would be X plus delta X, Y plus delta Y, and it does not satisfy this condition. You realize? You understand? So now, so what am I doing? I'm not going there. But so what I'm doing is I'm staying where I am. Okay, so I stay where I am. But now, okay, so here's my circle. So if that's not the case, then I'm staying where I am. I'm staying where I am, and I'm computing. I'm finding out whether x squared plus y squared is smaller than 1. And if it's like this, then I say the number of hits has increased. You understand? So now what's happening if I have rejected the move? So this is called a rejection. If I have rejected the move and I put second, do I count the n hits again, or don't I? Do I count the hits again, or don't I count it? No, don't count, right? And that's wrong. So I think you have to count it again. So I think we have in 5 minutes. How much time did we spend? 53. So we are okay. So we have spent a little time, and we are already at the first thing that we don't understand. So let me tell you what is happening. So let's say the exercise for some of you, for all of you, the exercise, program this algorithm. Try to compute pi over 4, because that's what we want to get. And then make a picture of the samples that you obtain. And let me just tell you immediately what is the picture. So it's like this. So in direct sampling, what we had, we can do it in, so the first case was what's called direct sampling. We have pebbles uniformly distributed, and they compute pi over 4. Okay? In the second case, we also have pebbles. I mean, we have little points, samples, examples of the probability distribution. And they are very funny, because we have pebbles uniformly, but outside here, I have 2 pebbles on the same side. Here, I have 5 pebbles on 1 point, because I threw 5 pebbles and I put them on top of each other. So the picture looks like this. Okay? You understand the picture I'm drawing? Right? So it's at time t. So, okay. At time t, I was here. I threw a pebble outside. I rejected it. I went here. Time t plus 1. So this is at time t plus 1. This is at time t plus 2. And I rejected. So I have it. So now, what I can tell you is that the distribution of samples, of pebbles on this square is uniform. It's strange, right? I count many I count them. I count 17 pebbles on the same side. And what I'm saying is that pi of x and y is uniform. And pi over 4, excuse me, I use pi and pi, so the number pi over 4, 0.78, will come out only if you count 17 pebbles, all the pebbles on the same side. We have the whole week. We have the whole week. So, but it is true. So in a more complicated example, this was proposed in 1953 by Metropolis. And what happened, again, I'm completely without humor, as you will know, we'll find out. So in 1953, they said that this is like this. And then people didn't say you have to prove it. They said this is wrong. So they were... Exactly. So then everybody said this is wrong. This is wrong. They sent letters, across the Atlantic and so on and so on. I mean, I have the whole, I have the whole story. So there were letters sent, and at some point, there was no solution to be found because there was a big field of big experts in mathematics who said that this is wrong, and the other side that said this is correct. And then they said, well, this is called the Markov-chain. It's a little bit like excuse me. It's a little bit like bosonization. Nobody understands how it works. Then they said, yes, this must be true. Okay. All right. So we will spend Wednesday, because this is the introduction. Wednesday, we will spend on proving this and even going beyond this concept. But because it's Monday, I think a good way of actually getting confidence that this is true is simply to program it. This is 5 lines, 7 lines, okay? So what I'm saying here is the following. If you take this if here, and put it into this thing here, you make a mistake. You understand this? So try it out. This is the if. You count it even if you have rejected the move, okay? You see it here? You understand? So if you have this if here, it's on the same level as this here. Even if you have rejected, you count again. And you can check it. You put it 5 lines in. You only count it if you just newly arrived, if you moved actually. And you'll find out that pi over 4, then you look up. Well, we will ask one of the local experts. It will be another distribution, which will depend on delta. Yeah, it's a distribution, of course. It will be a distribution. What it will happen, it will be a distribution which is going to be delta dependent, little delta dependent, and which will be almost 0 at the boundary. Okay, so now maybe we could have, maybe I continue a little bit, if you agree. But for example, it would be really interesting if during the next 2 days, you answer, first of all, you find out whether we can come out with pi over 4, and you make little histograms of what is the distribution if you put the if here, and what's the distribution if you put the if here. But the statement I'm making, we will prove it on Wednesday. We'll go beyond it much far because you didn't make me come here to prove something about 1953 physics, right? Okay, so you would send me back to Paris immediately. So I want to be more. But the statement is the following: that we are having a model of equilibrium. We'll discuss that in detail, of equilibrium statistical mechanics. And for any choice of delta, you see the little delta here, because I didn't tell you what delta is. For any choice of delta, it being 0.001, 0.1, 0.1, 10, 100, 1,000, a million, for any choice of delta, we will obtain pi over 4. Huh?
Delta should be smaller than 1.
No. So you have a lot of work here, right? Okay, I think I cut off this here into a grid, and now delta doesn't have to be smaller than 1. We are doing something very simple, but it's so thought-provoking, right? So delta can be anything. So I ask, let's say this row to run it with delta equals to 1,000. you make piles. It will just, you make, so I mean, but maybe we can have a report on this on Wednesday, okay? You have delta equals 0.001, 0.1, 1, 10, 100, 1,000. And you know, I think we should understand this if we are then using these methods in quantum field theory or in huh? Okay. So the question came up. I said that this is a system of equilibrium statistical mechanics. The question was why is it equilibrium? And we'll discuss that also because the algorithm that is behind it satisfies the detailed balance condition. That is what we will show, and we will make the connection. But we are already completely confused, right? We are exactly where I wanted to get you. All right. So in former times, we would build little groups with people actually programming and coming back with reports of whether what I'm telling you about this delta being 1,000 can be correct or it must be wrong, right? I mean, but you know, you should take action to find out. So please take action. Take action to help me. I don't want to say against, but facing the doubters. Okay, so please take action. I mean, I've had two multi-sections. Okay, so anyway, so that was problem number 2. So you can take delta. You may do it yourself. I mean, not with ChatGPT. Please, program it for delta equals 1,000.
But I believe you.
Do you believe me? No, you just want to get out of the limelight. He wants that I discuss something, move on. Yes, you're not convinced, right? Okay, go ahead. That's a good point. So the question was whether it takes much longer until we reach pi over 4. And the question is longer than what? So what I tell you is taking delta equals 0.0001 is about as bad as taking delta equals to 1,000. But in the limit of t going to infinity, in all these cases, if you make sure to count the samples again, you'll do it again. All right, so now let's do the following. Sampling so we continued. All right. I mean, we could stay with this also if you want to, but maybe, otherwise, then I have to reimburse. If we stay with this thing here, then I have to reimburse last night's hotel because then, Galileo Institute will say we didn't make you come for this. So I have to go further. So let's do sampling again. So we understand already we have a distribution pi. And we don't confuse it with pi and pi. 5 minutes? Okay, so let me do the following. We have a distribution pi of x, and we can compute an integral like doing dx pi of x O of x. Integrals like this can be done like 1 over n sum over I O of I if O is distributed like pi. That is called sampling. Okay, you see it? So we want to do an integral like this, dx pi of x, O of x. What was O of x in my example, gentlemen? Huh? Speak up.
It was 1 if it was inside
And that is called a random variable. Okay? So always the random variable. What is this square? That is called the sample space of my probability distribution. So we have a sample space. On the sample space, we have a function from the sample space into the real numbers, which is called a random variable. Thank you. And this is the probability distribution. And on the left side, did I forget the pi? Is this formula correct? Yes, thank you. It is if pi is distributed. So on the left side, we have no pi explicitly in there because the samples I are taken from that probability distribution. Okay, so that is what is called sampling. So the i's are samples. I's are called samples of the probability distribution. Probability distributions, or because it's so related. You understand that sampling, or that is the same. It's also called samples of the integral that we want to do. So now let me do in the last 3 minutes, Mr. Chairman. In the last 3 minutes, let me do the following. Let me look at another example of a probability distribution, which is a discrete probability distribution. So you have 1, 2, until n. I have n points, and they are distributed with a probability pi of, okay, which is given by the height. So pi 1 is this here, pi 2 is this, pi 3 is this, pi 4 is that. You understand? So now the goal is to sample from, or to sample that probability distribution. You understand the problem? So in my book, if you want to have something, I don't. So it's I call this the Saturday night problem. So this is the probability to do you on Saturday, to do your laundry, to do your exercises, to visit your family, and so on and so on. So you have probabilities associated with something that you want to do, and you want to do one of these things with the probabilities, independent probabilities, or with the probabilities pi of I. So algorithm number 1 that I still have the time to do, 1 minute, okay? So it's called rejection sampling, and it's procedure reject finite. I put it here, have enough space. So I have a pi max, which is given by the maximum of the pi I, but the pi k. K is a random, is an integer random number between 1 and n. Patrick, are you here? I have he always makes fun of me because I use so this is called epsilon, is a random between 0 and pi max. If epsilon larger than pi k, then go to 1. 1 is here. And then output down here is output k. Okay? So this is the following algorithm. I have minus 1 minute left probably. So the algorithm is the following. I throw pebbles here. Okay, I throw, you see I sample this probability distribution, this whole rectangle. I sample from the uniform distribution on the rectangle, what we did already before. And what do I do if I'm up here? I am larger than pi k. What do I do? What do I do? It's your break time. So if I throw up here, then I go back, right? Then I continue. I throw another pebble. I throw another pebble. And now what I do is here. So if it goes like this, then what I do? I output what? The index. The index. Okay, so n minus 1. So then my answer is this. Okay, so and this this event was take a break. Okay, so now we take a break. Okay. So let's continue on our journey, because we still have 16 minus 3 algorithms to do. Well, maybe we do a little fewer than that. Okay, so we had this discussion here. Okay, so let me do it like this. So this is a famous algorithm called the rejection sampling of a probability distribution. It's not the Markov-chain method, but it's a sampling algorithm. So you understand. So you know, it is so simple that I could actually ask you to put your mind into it and try to understand what it's doing. Right? It's simple enough, and I think maybe you understand this, that k is equal n run. You understand what I mean with n run, right? Integer random. So it's 1, 2, 3, 4 until n. Upsilon is a random number between here and here. So k is a random number between this and this. Upsilon is here, so it's uniform distributed. So you understand that the probability to hit this element k is proportional to the height of pi k, right? So we are not worrying about normalization issues, but let's say we kind of understand that this algorithm should output k with a probability which is proportional to pi k. Is this a good algorithm? Is it very much used? Yes. Yes. It's used zillion of times every second. For example, if n equals to 2, this is called the Bernoulli distribution. That's one of the ways that we sample Bernoulli. So rejection sampling is one of the most common uses. It's not the best one. And today, in the interest of time, I will not show you the best algorithm, but I'll show you a better algorithm. So this is the algorithm, rejection sampling, but it is correct. Do we agree on it? I mean, you need time to think about it. Do you think it's correct? So the question was, which criterion do I use? And the criterion is let's say, and if it depends on whether you want an empirical criterion. An empirical criterion is that the histogram, you run this for 1 billion times, or for 10 times, or for 100 times, and the histogram with which k appears, if you run this many times, should be proportional to pi of k. With some errors, but without systematic errors. So in the limit, so what I'm saying that in the limit of running this for fixed distribution and an infinite number of time, then we should have the same distribution. We should have an histogram which is like, which can get us. Thanks for the question. You understand that all these questions get us into very profound questions, for example, about what is the definition of a probability. So what we are doing here is we are using the frequentist interpretation of probabilities that I and particularly my friends from the mathematics department can give you year-long courses. And they are right to do this. But that's, for us, if we run this many, many times, the histogram will come out without any error will come out. But it's not the best algorithm, because a lot of the pebbles that we are throwing, every pebble outside of my skyline is lost. So a better algorithm, not the optimal algorithm, but the better algorithm is this one. What it does is I take probability pi 1 here, and I build a tower okay. So this is pi 1, this is pi 2, this is pi 3, and I introduce variables which is capital pi 1 here, capital pi 2 here, capital pi 3 here, and so on, and this is capital pi n. So now what I do is I throw a pebble between here and here. What I'm telling you is, again, we could formalize this in many ways, but the probability that it falls into this box here is proportional to the size of the box. So it's proportional to pi 3. And this algorithm means, so then I throw a pebble between here. So the algorithm is the following. I build up the integral of my probability distribution. So this is the integral. So you see it here, a discrete integral. We'll do it continuously in 2 minutes. I throw a random variable epsilon between 0 and the sum of the probabilities. So that maybe this could also be 1, I don't know. And then there is a little line here that find the k such that we have pi k minus 1 here, pi k plus 1 here, pi k here, and it falls into this pebble, into this thing, and then output the index, output k. Again, so for example, last week I had a 3-hour discussion with a friend of mine who is a computer scientist, theoretical computer scientist, about what is the complexity of this algorithm. I think the complexity of this algorithm is log of n, but he was very much opposed to it. And he told me that he once failed an exam because he said that the complexity of this was log n. I said, okay. So then we had a beer, and there was, so what I'm just saying here, so there's a lot of deep problems, but let's say for us, finding which one, where it falls, is not proportional to n, it's logarithmic of k. Anyway, but that's a correct algorithm. I called it tower sampling. You understand the algorithm? Okay. All right, so I have a probability distribution, a discrete, for the moment, I have a discrete probability distribution of n terms, pi 1, little pi 1, little pi 2, little pi 3. We understand this algorithm because it hits element k with probability pi k. So now what I'm doing, so this is probably pi 1, this is pi 2, and this is pi 3. Okay, so now I take a random variable between here and here. What I'm saying, so uniformly here, I'm saying it will hit this box with the probability which is the height of this box. It will hit this box with the probability which is the height of this box. So what I do is I have to compute this probability pi 1, little pi 1 plus little pi 2 plus little pi 3, and take a random variable between here and here. That's what I'm doing here. Okay, so now you believe me that it will hit this box here with much lower probability than this one. What is the rejection rate of this algorithm? Thank you. Do we understand that? So that's an advantage of this algorithm. Yes? Complex. Well, among us, if you're not computer scientist, we to find out where you are. So this is. You first have to you first ask the question: is it larger or smaller than capital pi n over 2? then it may be upper or lower. So what you have to do is, you have this thing here, you cut it into two, and you find out whether the pebble is down here or up here. If it's down here, then you cut it into two, ask whether it's lower or upper. If it's then, so then you have to do a bisection, and this bisection is, for us physicists, of complexity log n. Okay, let's. Yes, exactly. So, yeah, absolutely. So it is, because it's a bisection, not in probability space. It's a bisection in index. But there is an algorithm that I will not go into. Where is? Okay, so I will not get into the algorithm. There is an algorithm O of 1 for this problem. I will not do this now. Okay, so this is. Can we move on from this algorithm? Yes. O of 1. Yes. But then anyway, so it's a long discussion. So we can have this discussion later. So now let's do the continuum version. That's what I want to do now. Let's say we have a distribution like this, and we have a probability distribution pi of x, which is this. For example, this distribution here. If you want a title for it, then I call it. This title is sample transformation. You can look it up. You travel to Russia. You get the book there. You can look it up, but you can look it up many places. So we have a probability distribution, and we take the continuum limit of this algorithm. Okay? We take the continuum limit. So what we are doing, so this is the probability distribution pi of x, and then we have the function capital pi, which is this, between 0, let's say it's a distribution, between 0 and 1, let's say it's like this, just for simplicity. Then we have to make the tower. So this is the integral, okay? That's the function, that's the integral of the function, and we make a little tower. You can think it for yourself. Then what we do is we throw a random number between 0 and the maximum. This is the random number, and we have to find which is the x that it comes up with. So there is nothing complicated in what I was doing. But let's do it the following. Let's call this sample here, let's call this epsilon. Of 0. I'll explain to you in 2 minutes why this is a 1. Let's call this sample epsilon. That's this sample here. That's the sample. Do you understand that? That's not a probability distribution. In all of what I'm doing, epsilon is a sample. So I have this sample, and I transform this sample. So sample epsilon gets transformed into a sample of x. Epsilon is a sample of which probability distribution? Huh? Yes, what is it? It's the uniform distribution. And x is a distribution of pi. So what we are doing, in fact, is I have an integral. It gets very complicated now. We should have a break and all get some coffee and come back in 1 minute, but it doesn't work. So let me do it like this. That's the way we like to write it. If you think about it for a few weeks, months, or years, you find out that this algorithm here starts, epsilon is a sample. It's a sample of the uniform distribution between 0 and 1. Let's say the distribution goes up to 1. And we have a transformation into a distribution of x, pi of x. Now what I'm telling you is that this algorithm of the tower sampling algorithm is nothing else but saying d epsilon is equal to dx pi of x. How is this solved? It is solved by epsilon is equal to capital pi of x, which is the integral over dy pi of y up to x. And epsilon is a random variable a random number between 0 and 1. So now this is a function. This is a function of x, and I have to invert this function. Let me give you an example. Of something I actually believe in. Let's say we have a distribution pi of x is equal to x to the gamma. For x, let's say between 0 and 1, and gamma, it's not epsilon, larger than minus 1. So for example, so this is a distribution pi of x. This is x. And this is gamma plus 1. This is gamma plus 1 times x to the gamma. So now this is now we have a problem. We want to sample. I hope I'm not losing you. We want to sample point x with a probability which is pi of x, which is x to the gamma. How do we do that? So we don't take a random variable between 0 and 1. That's what many people take, and take it to the power of gamma. That's complete rubbish. What we are doing in employing our algorithm of tower sampling in some limit, what we are saying is the following. We write integral d epsilon from 0 to 1 is integral from 0 to 1 dx x to the gamma. Which means that epsilon is equal to x to the gamma plus 1. There are some constants and so on and so on. But now epsilon is a sample, random between 0 and 1. So what are we saying is that x is equal to a random 0 and 1. I'm cutting a few corners to 1 over gamma plus 1. So now I come to my little exercise. Procedure. Direct gamma. Which is the following. Epsilon is equal to random to 1 over gamma plus 1. That's my program. Output, excuse me. Epsilon is random between 0 and 1. You didn't write this down, right? So now you take x is equal to epsilon to the 1 over gamma plus 1. Output x. So this is a 3-line program. This is a 3-line program. What I'm telling you right? You can write this program. What I'm telling you is that if you do a histogram of the axis will be distributed according to which distribution? Huh? X to the gamma, and not x to the 1 over gamma plus 1. But you know, better be sure. Write this 3-line program, embed it run it many times, make a histogram, and check that it's true. But I guarantee you that this is like this. So what I'm telling you, claim X is distributed like a distribution, the sample xi is distributed like x to the gamma, but for x between 0 and 1. So xi is between 0 and infinity. Do we have an expert programmer here? Can one of you let's make a 3-minute just chatting about, can somebody program this? Okay, you're doing that. Let's stop here, and compare it to gamma plus 1 x to the gamma, to the function. So I'm just, because this is kind of, okay? So we have nothing to do because our friend is doing all the work. You understand what we are doing? Do you believe that the outcome will be okay? You hope so. But you understand? So what we are doing now is we are using a concept we are doing integral transformations, right? I mean, we have for many years we've learned in school that we need substitution rules, and substitution rules gave us integrals. What I'm telling you is that these substitution rules apply directly to the samples. At 4 o'clock I have to stop. We improve his productivity by performing, air conditioning. Okay. All right. So while you do this, let me start something else. Let me do. There's a function called I, which is the integral dx over 2 pi e to the minus x squared over 2. What is the value of this integral? What is the value of the integral? 1 or 2? 1, right? How do we prove it? We square it. Okay, you don't listen to us. You have a job here to do. Okay, so how do we say? We say I square is integral dx dy e to the minus x squared plus y squared over 2. And then, huh? Can you speak up? Huh? Polar coordinates. So what do? We say we have r is equal to, r squared is equal to x squared plus y squared. And phi is equal, and x is equal to r times cos phi. Y is equal to r times sine phi. You agree with this? So what does this turn into? It's integral over dr, r, e to the minus r squared over 2 divided by 2 pi times integral over d phi. Now what we do is we call r square is equal to u. and we have it integral du integral d phi over 2 pi. So now we know that this integral is equal to 1 and this integral is equal to 1, so we have proven our theorem. Excuse me, Gabriele, you've seen that before. Now I just forgot to say that once you are done, you take another integral. Okay, we have a good news here. All right, show it to everybody. So I'm not giving you. Huh? You believe me? Okay. So now they do the same thing with the same trick. You take epsilon is equal minus logarithm of random 0, 1 will be exponentially distributed. So now what I'm telling you is the following. I have a du e to the minus u is an integral. Integral d phi over 2 phi. So now what I'm saying is this integral can be sampled. How can we sample phi? Huh? So phi is so now we can write it the following. We can say phi is equal to a uniform between 0 and 2 pi. You agree with that? We can say u is equal to minus log run of 0, 1. I cheated a little bit because I didn't prove that. Okay? So now I have sampled this integral. And I have sampled this integral. Now what do I do? I say x is equal to now I say the following: r is equal to square root of 2 times u. Okay, r squared over 2 was u, so I do r is equal to this. Then I do x is equal to r times cosine phi. I do y is equal to r times sinus phi. What's the distribution of x? You see this algorithm here? See, I really feel useful now. See, I had an integral of dx dy. I made a bunch of substitution rules that brought me to u and phi. That's what we learned in high school, or in depending on where we grew up, in high school or in first year university. So then, huh? No. Can we have another? Can we have somebody program this thing here? The question is, you program this algorithm, 5 lines. You run it many times, and I want to know what is the distribution of x. It's a Gaussian. It's a Gaussian. Why is it a Gaussian? because we've used the principle of we have used the substitution rules. We have used 3 or 4 substitution rules and applied them to samples. So we could have started with samples x and y Gaussian distributed, and we would have obtained 2 uniform distributed u's of x. If we go the other way, we start with uniform distributed u's and phi. We carry them through our analytic calculations, and we'll have Gaussian random variables. But maybe you do this for yourself. So now, I have many more things that I want to do. But in the last 5 minutes, let me start with the beginning of your question of in which sense do we actually do a correct calculation. Let me show you. So now, let's say I have an integral that I call integral of gamma is equal from 0 to 1 dx x to the gamma. It gets very confusing now. What is the value of this integral? Okay, thank you. 4. Okay? So we know this. So for any gamma larger than -1, this is a correct formula. Whether we do it in Riemann or Lebesgue, in France or in Italy or whatever, that's a correct formula. Now let's do it through a sampling approach. But I will connect it to the question that came up before. So how can we sample this integral? What does it actually mean? So what it means is the following. I write here a probability distribution pi of x, which is equal to 1. Okay? So I have x's, which are uniformly distributed between 0 and 1. So let's write this program. I take x. Let me do it like this. Let me do it like this. Let me do it like this. Upsilon is random from 0 to 1. This samples this integral. So now what I do is x I for I in 1 to n. I say xi is, what is it? Upsilon to the power of gamma. I start here with the sum is equal to 0. And I say sum is equal to the sum plus xi. So what I'm doing is I am sampling the interval from 0 to 1. It's a random between 0 and 1. I take it to the power of gamma. I compute running values, and then I output here, for example, sigma divided by I. So this is a running average of the distribution, running average. So this is the running okay. So now let's take, you still have 3 minutes? 5, come on, 10 minutes, half an hour. No, just 3 minutes. Okay, do you understand what I'm doing here? I take random between 0 and 1 to the power of gamma. I run it many times. I'm not doing Markov chains here. I'm doing something very, very simple, but we'll get all completely confused very quickly. So don't worry. Okay, we do this. We add the terms and take the average. Let's run this for gamma equal minus 0.8. Does the integral exist? Yes. So now, again, we can have an exercise. We plot as a function of time, iteration I, we plot sigma divided by I. Here is 5. Okay. If you run this, I mean, it's 5 lines of code. It will teach you something, I mean, it will teach you completely fantastic things. So I'll tell you, it will look the following. The other day when I ran it, it looked like this. And then I stop. This is you do it yourself. It's 5 lines of code. And you understand what you have to do? You take random variable to the power of gamma, you sum the terms. And now I tell you the theorem, which is called the strong law of large numbers. The probability that limit from I going to infinity of sigma I divided by I, that is, this is given by 5 is equal to 1. That's called the strong law of large numbers. We will discuss the Markov-chain version of this theorem in on Wednesday. What this means is the following. So, I mean, do it yourself. You'll see it looks like this. In the limit of I iteration going to infinity, this will converge towards the analytic value. But what does this limit mean? What does it mean that the sum has a limit? For any epsilon, right? We learned that in school, right? For any epsilon, there is an I such that for any epsilon, there is an I. Good, you went to good schools, right? All right. So what does it mean? That's called the strong. It's completely mind-boggling. For any epsilon, for example, this epsilon here, there exists an index I of epsilon such that for all later times, you'll never get out of it. This is with probability 1. So what this means is something that many people don't understand, even when they have spent a whole life on this thing, is and have I done an average over my histories? No. I'm doing a single iteration. I'm doing a single run of this thing going in time. And for a single Monte Carlo calculation that I'm doing here, I am assured that for any epsilon, that the limit exists with probability 1, that the limit exists, that for any epsilon, there exists an I such that you formulated it, right? I never get out of it. That's called the strong law of large numbers. I wanted to discuss it here. We'll see it again as the ergodic theorem of Markov chains. Very, very strong convergence. You know, it's not on average, it's not maybe, it's with probability 1 for a single simulation. The probability is 1.
Yeah, but probability means that it's not a real limit. It's a
No.
limit in probability.
No. This is almost sure convergence. Oh, thank you. Did you hear the comment? Even though I ran over time. So the question was whether this was a convergence in probability. And it is not. This is, we can discuss this on Wednesday. This is almost sure convergence. In probability means that all histories, when you do all histories, I had prepared, but I didn't have time. So that's been probability. That means that a single trajectory of a Monte Carlo simulation will converge towards the right result with probability 1. So this is, let me just put it here. This is called almost sure convergence. And this is much more stronger than a convergence in probability. It implies anyway, okay? Well, because there can be, where's the code? Here. It could be that each time, you know, with a probability 0, you can at each time you get 0.8. You know, there could be 0.8, 0. You understand? This probably you can produce sample. You know, with probability 0, you at each time choose the same random number 0.8, 0.8, 0.8, 0.8, 0.8, 0.8, and then you get the wrong result. I think you're looking at me, you know. Now I have to stop. Okay, thank you very much for your attention.